So there's no net dipole, therefore the molecule is non-polar. We go over here to CCl4. So let me actually start right this time and say that carbon has 4 electrons and chlorine has 7 electrons. So 4 plus 4 times 7 is 32 electrons. So it's kind of ugly right here, so I drew a more clear picture for the first part. Draw the bonds between the carbon and the chlorine for each of the 4. So that's 8. Then load up the outside. That's 1, 2, 3, 4, 5, 6 for the outside, for one of the outside chlorines. So if there's 6 on the outside, and that means it's going to be 6 times 4, so that's 24. And 24 plus the 8 for the bond electrons is 32 electrons. So it's looking like we're pretty good. So we go to the electronegativities. Step 2 is identify the bond dipoles using differences in the electronegativities. So for carbon, we have 2.5, and chlorine, we have 3.0. So we start from the... okay, so we start from the central carbon, and we go towards the more electronegative chlorine for each of the sides. So with that in mind, we point to the outside, and so it's pointing there. There's 4 domains, so the domain geometry is tetrahedral. So then we go down here, and we can see that it is indeed tetrahedral. And the molecular geometry is tetrahedral because all of the domains are bonds. Since all the domains are the same, it is tetrahedral. Yeah, this one was pretty easy to do. 4 domains are exactly the same. There is no net dipole, so the molecule is nonpolar. Yeah. Sorry that my sweet mates made some lovely gestures that kind of threw me off for that problem. I apologize. Oxygen 3O3. I'm getting tired of doing this. Let's get this done. We got 6 electrons for the oxygens. That's 18 total. Electronegativity of the oxygen is 3.5. So over here we go. We do the bonds from oxygen to oxygen. That's 4 of the 18. So then we load up the outside. That's 6 and 6. 4, 6, and 6. That is 16. So we need 2 more. So we load up the 2 more on the central oxygen atom. And then, but we see here that the oxygen does not. This does not have an octet. So it becomes, instead, we take one of the outside non-bonding electrons and we make it into a bond. So then each of the atoms has an octet. And so the next step is to identify the bond dipoles using the differences in the electronegativities. Well, the electronegativities are 3.5 because it's all the same atom. It's just oxygen. But the thing is, when you look and see what it is, from the Lewis structure, you have 7, 6, and 5 electrons. So that means the central atom is the partial positive, and then the outsides are the partial negatives. And I think I forgot to mention that for the previous one. The central is a partial positive, and the outsides are the partial negative. So that's why the arrows are going towards the outside. So we have that in mind. There are 3 domains: trigonal planar domain geometry. There's 1 non-binding set of electrons. That means it is a bent molecular geometry. So you can see that here. You have the step 3 is identify the net molecular dipoles based on the molecular geometry. This is the domain geometry. We have the non-binding pair on the outside here. But then you jump over here to the bent molecular geometry, which is what it is. And you have the bond dipoles pointing to the outside. There's a net going towards the bottom. So there's a net dipole so the molecule is polar. And then this molecule also has resonance because you can make the double bonds on either side, and then you can see that there's the dashed lines for indicating that it's going to switch back and forth constantly. Okay, and our last step is to identify the mistakes. So there's a mistake for each one I pointed out. For the original SO3, the mistake is thinking that it is a 2 to 1 to 1 instead of a 3 to 1. There's a 2, 1, 1, a 2, 1, 1, instead of a 3, 1. There are 3 that are 1/3. So you have a third, and a third, and they're all of the ones, the bonds are equal, and that's in real life they're going to be equal. It's just going to be jumping around as it's just continuous. So the mistake for the second one, which is the OF2, is the mistake is that is linear instead of bent, and the mistake you would make from that is you have these two outside non-binding set of electrons, which force it normally would be linear, but they would force the angle of the force to go down, therefore creating that bent pattern. So for the BeCl2, the mistake is kind of ugly, but it says altering the Lewis structure to make Be have an octet. So we go up here, and this is what I was talking about. And Be doesn't have to have an octet because it is an exception to the rule. If you did not know that, you would be trying to make these two go into a bond and then these two go into a bond to make sure they all have octets. But that is not necessary because Be doesn't have to have an octet. For the CCl4, the mistake is just in the drawing the net molecular dipoles is just saying that there's a net of going down. I could see how you could mess up by drawing the tetrahedral on a 2D paper. You see that it's down. The top and the bottom would cancel, but then there's like the two down, so you can maybe see how it would be a net down. But you have to remember it's tetrahedral, which is 3D, so just the way that tetrahedral is, it's going to my brain's fried. You know what I'm talking about. It's tetrahedral, so they're all going to cancel out. So yeah, the mistake for the final oxygen O3 is trying to draw it like this. And if you see it actually makes sense when you draw it like this because they each have they all have the octets, and then they all have how many electrons they want. But this can't work because the angle of the bond is too strong, and therefore it's unstable. So basically, as the oxygens are together, and then this bond is reacting with that bond and that bond, it's just a very unstable structure. Therefore, it falls apart. So I think that's it. So then we go back to the original thing, and we say, how many of the molecules are polar? So of the 5, we have the OF2 is polar, and the O3 is polar.